Okay, so Ampere's law part 3, more examples. We have done the example of a thin sheet, infinite sheet, and then 2 infinite sheets, and came up with the field above and below the infinite sheet being mu, infinite sheets being mu naught j. There's no 2 because we have 2 sheets, and in between is 0. You can easily prove that for yourself. Okay? So I won't go through that right now. What I'd like to do now is, let's say that you have an infinite conductor, circular conductor, with current density, uniform current density pointing into the board like that. So, and we'll do an example with non-uniform current density to see how that works. Right? So the current density is uniform, and it points into the board. Current density is J. Right? What I'd like to do is calculate the field, the magnetic field inside and outside the this wire, and we're assuming that this has relative permeability of 1. Okay? We had done stuff like that with uniform charge distribution in a sphere, tried to find what the electric field was inside and outside and whatnot. So let's try to, well, I mean, current density is uniform, J. So what is the current flowing? The total current flowing through this thing is I is equal to the integral of J dot ds or dA over this, and that's equal to J is uniform, so it's J times pi r squared. Okay? That's your I. Okay? J is J naught, it's uniform, so fine. Now what is the field outside here? Well, we're gonna do, we're gonna draw an Amperean loop, and the only thing we're concerned about with symmetry for Ampere's loop or Amperean loop is what? One more time, just like Gauss's law. The field, the magnitude must be uniform over the loop, and the field direction must be constant relative to the loop. So because of symmetry, this is uniform current distribution. I'm gonna pick a loop like this. Why? Because I know that the field over this loop is gonna maybe look something like that. Going like this, so you point your finger into the board, that's where your current is going, and your magnetic field is going to look like this. This is B, 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 okay, all over, and DL, B, got more B's, right, and B this way. So DLs are going to be along the loop, so this way, so we basically integral of the angle between B and DL is always 0. This is great. Now the integral of B dot DL along the contour is equal to mu naught I enclosed, and that's equal to what? Well, B is, this is the integral of, it's always good for the first few examples to lay this out on your own too, when you write this down on an exam, exams are probably going to be multiple choice. Assessments are going to be also multiple choice, most likely. Right? Still haven't completely decided that yet. And things are going to run at the same time as they're supposed to run. For example, your tutorials are on Monday, 1:30 to 3:30. That's when the quiz is going to be open and closed. And the final exam is going to be conducted during the same time as the final exam. But there's details, I'll let you know about that later. Okay? So it's good for you to practice, despite the fact that you're not doing this maybe on an exam. If we go with a multiple choice exam, is it good for you to get out of exam mode now? Okay? Don't worry about the exam, right now. Okay? You can worry about it later. Right? Don't freak out yet. Right? So integral of B dot dl is B dl cos theta. The angle is always 0 because of this business. So that is one. It's always good for you to lay this out like this, write the full magnitude. I know it's boring, I know it's, write it out, the magnitude bars, and write out the proper dot product, scalar product. B, this becomes, okay, now we can get lazy if you want. This is BDL, okay, but we understand that this means magnitude, and that's equal to, well, B comes out of the integral because, well, we've gotten rid of cosine theta as 1, and B is uniform, so this is B times integral of dl, and that's equal to B times 2 pi r. We kind of, did this, this is radius r of the Amperian loop that we picked, right? We were kind of lazy in the problem with the infinite sheet that we didn't actually get it to this point. We wrote B integral of dl as equal to B times dl, B times L, okay? Remember with the infinite sheet, we had, drawn an Amperian loop like that, and I said it verbally, I didn't write it down, that the integral of b dot dl, 0 here, 0 there, 0 there, 0 there. Up here it's the integral of b dot dl, that's b this way, dl this way, cosine theta is 0, so 1. So it's just integral of b dot dl, and b is uniform, b comes out of the integral of b dot dl here, also b dot dl was equal to integral of b magnitude dl magnitude cosine 0 in this case. We're just talking about the top part, right? So for the top part alone, b came out of the integral of dl, and that thing was 1, so that became b times l. So you had one of those at the top, okay, and one of those at the bottom, one here. So this is just for the top, okay, and for the bottom you had b integral of dl equal to b times l as well for the bottom, if you missed that, okay. So that gave you 2bl, okay. So I'm saying that now because I did not really lay it out like I did here. It was kind of obvious that b is uniform over the top part of the loop, so it just, you know, comes out of the integral. Integral of dl is just l, bl, another bl, 2bls, top and bottom. I'm just bringing that up now because I did not really do it that way and didn't feel there was a need, but if you missed it, here it is. So now we go back to here. Integral b dot dl on a closed loop is b this way, dl this way, angle is 0, so we get b times 2 pi r. So what is that equal to? Integral of b dot dl is equal to b dot dl becomes equal to b times 2 pi r. And we know the integral of b dot mu is equal to mu naught I enclosed. That's equal to mu naught times I total. Okay, I total. So really, what you have outside, b is equal to mu naught I over 2 pi r. And what is I? I is given by that. We're not going to worry about it too much. But the idea is that b goes as 1 over r outside this wire. Okay? So now pause for a minute and see if you on your own, stop this video for a minute please, and see if you, on your own you can calculate the field inside. So this is what we call this what? This is for r greater than r, okay? On your own, try to get r less than r. What is r? R is the radius, capital R is the radius of this conductor. Okay. So please pause and do that. So to calculate the field inside the conductor, what I'm going to do again is draw an Amperian loop. Because of symmetry, I know the field is going to look something like this. Okay, so I'm going to draw my Amperian loop here. Radius little r now. See, little r, doesn't matter. Just dummy variable. So basically, my Amperian loop is here, and the enclosed current is there. That's where the calculation is going to be right now. So we go along this Amperian loop. Which way does the field point? Again, because of symmetry, it points this way. B is going to be like this, and dl is the same way too. So there is no harm in you stating now for r less than r, the integral of v dot dl is equal to mu naught I enclosed, okay? And that's equal to what now? Well, b is, well, we picked an Amperian loop whereby b and dl are parallel. So that's the integral of, no harm in, again, spelling it out, b dl cos, the angle between them, theta, is equal to mu naught I enclosed, okay, and that's equal to the integral of, well, b is, you know, b, dl, these are again magnitudes, but I'm being lazy, and that we have actually laid it out. We don't have to keep writing magnitude bars and vectors. You want to go ahead, it's a good practice. And cosine angle is 1 because angle is 0 between the two, and we get that this is equal to mu naught I enclosed, and that's equal to what now? Now here we have to be careful. I enclosed in here is the integral of what? J dot dA or ds, okay? From 0 to, or over the, you know, over the Amperian loop. Okay, we're not going to parameterize that yet. Okay, so that B comes out, and you have the integral of dl. Okay, that's just 2 pi r, so that's B times 2 pi r equal to mu naught integral of what now? J is equal to, well, J is J naught, right? J naught times ds, that's up to you how you want to do this, okay? But it's uniform, so really there's nothing for us to worry about in this case. That's just going to be equal to mu naught times J comes out, integral ds is pi r squared, J naught times pi little r squared, okay? We're taking, this is just the area of the you know, area enclosed inside the Amperian loop that gives us, this is the current enclosed, right? So the field inside for r less than r, B equals to mu naught J naught times r over 2. Okay. All right. So yeah, bi's cancel, 1r cancel. So this is mu naught J naught r over 2. So what do we get from that? We get that the field, if I was to plot the field as a function of r, so this is my conductor, right? And I'm going to set up my coordinate system so that, you know, I'm going to try to plot the field B as a function, the magnitude of B as a function of r is going to grow linearly. If you're asked to plot that, it's going to grow linearly in this region until it reaches here, and then it's going to go as 1 over r. And you should really label that this value is what? That is the value of the field at r equal to capital R. That's equal to mu naught J r over 2. Interesting to note that you can get this value either from, you know, approaching from the inside or the outside, which give you the same value of B. Right? So this is R. All right. So that's a simple example of uniform current density.